Okay, so let's do a little regression theory, okay? So again, my interest in regression is as a description of population relationships. I understand that when you run regressions, you're going to use samples and you need a little bit of statistics. And indeed, I'm talking about standard errors. And there's all these annoying statistical issues. Somebody mentioned clustering. Yeah, clustering is the worst. So I don't want to talk about any of that. Okay, I want to keep the focus on clear-cut things, okay, conceptual things. So the thing that's of interest to me today is population regression. And population regression can be described in a few ways. And then I want to just quickly review some of the key properties of a population regression vector. So I define population regression as the theoretical best linear predictor. So there's some variable y, and you're going to use a linear function of x. And now I'm not distinguishing between the x's. For the purpose of the theory, I'm not distinguishing between the x's. I'm just defining that coefficient vector, okay, b. And so I apologize for the sort of mix-up in the notation there. So here's the here's the population best linear prediction problem. Minimize the expectation of the squared errors in the population. Then there's a first order condition for that. And of course, the first order condition for that is really saying the residuals should be uncorrelated with the x's. That's why it's meaningless to ask whether the residuals are uncorrelated with the x's, because that's what regression does. It produces that. That's its first order condition. Well, if you manipulate this, do a little bit of algebra, you find out that, linear algebra in this case, you find out that the answer to that is beta. Again, this is not an estimator. It's a feature of the distribution of y and x is equal to e of x, x prime inverse e of xy. So that's my population regression vector. And again, not to belabor the point, but there's a lot of confusion on this. The residual here is 0 by construction, by definition. So this is a feature of regression. It's not an assumption. You can't use this fact to decide whether the conditional independence assumption that gives your regression a causal interpretation is true. Because regression will always do this. Whereas the question of whether you've got good conditional independence assumption, that's more conceptual and has to be thought out in the context of institutions, okay? So the residual is by construction uncorrelated with the regressors. EI owes its meaning and existence to beta, okay? So there's some subtlety there. It gets a little scary. There's even a movie about it. So let me give you my version of the movie, okay? So why is regression such a beautiful, powerful thing and such a great way to summarize relationships? So one thing is it does have this predictive feature. It's the best linear predictor of y given x. So that would be one reason why you care about it. Another is that, if it turns out that e of y, that's the conditional expectation function, so e of y given x, if e of y given x is linear, okay, then regression is definitely that, okay? So if there's some b for which e of y given x equals x prime b, it's my beta, okay? So regression coincides with the CEF. And there's some classic cases where the CEF is linear, like dummy variables. We'll come back to that. And another classic case is normally distributed variables, which is less relevant. Okay, but my favorite reason, and this will spill over and connect back shortly to what we're doing. My favorite reason to love regression is not only does it solve the best linear prediction problem for y given x, but it also solves a best linear approximation problem. So you can think of e of y given x, that's kind of an awkward thing. That tells me how average y varies as a function of x. And there's as many values of that as there are x. So if x is something like the vector of controls in the Dale and Kruger, there's potentially thousands of values that those regressors take on, SAT scores and everything kind of cross-multiplied with each other. So I'd like to summarize that with some linear approximation. Regression is the solution to that. In other words, the problem predict y given x, predict y given x, and the problem predict e of y given x, those have the same answer. Okay, so you can either think of regression as actually predicting y or as approximating the conditional mean function. What do these properties depend on? Trick question. Nothing. They're tautological. Regression is defined to have these properties. Okay, so this is, again, I think this is a source of confusion in the classical kind of playbook, okay, where we teach our students a lot of I would say distracting or at least not harmless, tools and ideas. And we tell them, for example, that, there are times when you shouldn't run regression. Give me an example of that. Do you remember that, Kiana?
When the error term is not, it's not independent.
Well, but it is here by definition. So that isn't going to happen.
When it's nonlinear, when the relationship is nonlinear.
Well, but I'm approximating e of y given x. What about if y is Bernoulli? What if y is a dummy? Can you run this regression and all this works?
I don't believe you can.
But you're wrong. Because what does this depend on? Nothing. Suppose instead of wages, it's a dummy for employment. You might think, oh, I should do probit or something. Everything I've told you is just as true for a dummy for employment as for wages. Regression is a very robust predictor of outcomes, and it doesn't matter what the support, what the distribution of the depend. It always fits the conditional mean function as well as possible. It always predicts y as well as possible, and y can be Bernoulli or non-negative or whatever. So there is a lot of distracted econometrics, I would say, that goes into worrying about scenarios that are said to be exceptions where regression is inappropriate, but I don't think that's true. I think regression is always appropriate. So, we'll see that in some examples later. Now, there is a thing that some regressions are stupid, meaning they don't really capture causal effects or they don't have the interpretation that you would like them to have. That's your fault. Okay, regression does what it does. It's just a formula. Okay, the question of whether it has a causal interpretation, well, you may have not come up with very good controls, okay? But that has nothing to do with the mechanics. Now, let me show you something else that's kind of cool about this. The fact that the solution to this problem and this problem are the same actually has, whoops, maybe you can't see that. So the solution to this problem and this problem are the same. So in other words, approximate e of y given x and predict y has the implication that you only need conditional means to run regressions. So here's an example. It's stylized, but it's real data. This is a regression of log earnings on schooling. So this is one of the labor economics, greatest hits. You regress log wages on schooling, and each year of schooling is associated with higher earnings. This uses data from the 1980 census. And in 1980, the returns to schooling measured this way, the economic returns to schooling measured this way were about 7%. Okay, each year of schooling was associated with about 7% higher wages. It's super precisely estimated. There's the robust standard error and there's the old-fashioned standard error. Okay, it's super precise. The standard errors are very low, because there's 410,000 observations. So there's nothing interesting here in the statistics. It is a big sample. By the way, the returns to schooling have gone way up. Many of you will know this. So now a year of schooling is worth more than 10% typically. I don't know if this is causal, but as an associational fact, okay? 410,000, 409,435. Okay, but here's another version of that, and you can see it here. instead of running the regression, I could compute the conditional mean function. So here are the points on the conditional mean function. Each one of these, this is e of log y given that s equals 4. And I'll put a hat to show you that it's a sample quantity. And this is e of log y given that s equals 14. And this is, and you could see it's not perfectly linear, okay, but it's sort of loosely linear. And then this is the regression slope. That's a line with the slope equal to the regression. And you could see that it interpolates those points. It threads those points. So it looks a lot like, instead of working with the data, I could work with these conditional mean functions. And the conditional mean function has 21 data points instead of 410,000 data points. So I could run this regression instead of that other regression. You could see there's nonlinearity here. So here is, graduating college is good. So the slope is higher between 15 and 16. Here's that third year of graduate school, not so much. Okay, this one actually negative, okay? Well, but later you'll make up for it, though not perfectly. Okay, so it sort of looks like those two regressions should be the same, and they are. So here's the 409,000, and then this one is y bar s. There's 21 of those. No schooling, 1 year of schooling, up to 20 or more years of schooling. Algebraically the same. So this shows you that regression is tightly linked to the conditional mean function, okay? And it's just a way of thinking about fitting averages, fitting a model for averages. The causal interpretation of the model for averages is a whole nother story that we'll come back to, that I've diverged from for the moment, okay? So I'm doing some mechanics here. There is a trick. What did I have to do to get these to work out? There is a trick. There is a trick. You can see it on the screen. What do I have to do to get these to work out? So everybody see that they're the same? It's kind of faded, but they're the same. 0.06847. What do I have to do? I have to weight. What do I have to weight by, Denny? The cell size, right? So that A weight, to get that average one to be bang on the other one, I have to count how many people are in each of the 21 cells. Okay, everybody see that? So to get it to work algebraically, there is a big payoff to this, and I've used this in my own empirical work. Sometimes you want to work, with tax data or something, and you have in mind that you're going to run a regression with, administrative data. I've used Social Security data to study the effects of serving in the Army, the military, on earnings. And I need a large sample of veterans and non-veterans, and that can be hard to get. And so I work with Social Security data, which has earnings of all Americans who are covered by the Social Security program. But they're not allowed to release the individual data because it's against federal law to release data that collected for tax purposes. And I say, well, no, that's fine. I don't need to know the individual person. Just give me the cell averages, and I can run whatever regression. So you can negotiate a disclosure process that satisfies confidentiality and still lets you do all the empirical work that you want to do. Regression has that property. Also, instrumental variables has that property, that conditional mean functions are enough. Okay, let's do a little bit more of the theory review, and that'll close out the day. So one thing I mentioned, there's something special about dummy variables. One of the reasons we love regression is they fit conditional mean functions when they're linear. And the most important case of linearity is a dummy. So think about a dummy, for public or private school. So then the conditional mean function as a function of that just takes on two values. Let me call the reference group, which is, say, public, alpha, and then the difference between public and private, beta. Well, that is going to produce a linear conditional mean function. It's a linear function of D. E of y given d is either E of y with d switched off or the difference between the two of them, which is beta. And so that's linear in parameters. So all dummy variable models have this feature that if I have a dummy coded for every possible value in the conditioning set, here there's only 2, then regression fits that conditional mean function exactly. Now, this brings us to something like back to the private case. What about the public-private model here? Okay, so this is the Dale and Kruger model. Now, this is less obvious, I think, and may not be familiar to you. Let me get rid of these regressors, which are continuous. How should I interpret a regression of log wages on P when I have all these dummy variable controls for the selectivity groups? And the answer is that is actually a weighted average treatment control difference. And there's a formula for that. So let me skip back ahead. So that regression produces a weighted average treatment control difference that can be written like this. So at each group, compare compare private and public, and then weight. And in this case, the weight is the conditional variance of the private dummy for each group. So you could think of regression as a kind of a matching estimator, where I'm going group by group, just like in my original table with the 4 groups, and then there were only 2 that I cared about. And then I'm going to go within each group and then weight across the group. So that sounds kind of like labored. And how would we get Stata to do that? Well, the way you get Stata to do that is you run a regression. Okay, and that's what you get, actually. And that has all kind of interesting ramifications, like statistically, this is the efficient thing to do when the model has constant effects. Maybe it does, maybe it doesn't. You want to do something else, but you should certainly start with this. Okay, let me give another couple of quick recap ideas, and then we'll go back to the empirical work. So one thing is, how should we explain regression to our students, and how should we think about it? You know, for me, it's kind of a point of pride. Many of you, probably most of you, have PhDs in economics, and so you will have learned, you know, regression with linear algebra. And you'll know that, you know, beta hat is equal to x prime x inverse x prime y. And that annoys me because it's very opaque. What is going on inside x prime x inverse x prime y, you know? If you have to invert that, it's very complicated. So I don't use linear algebra in my teaching, also when I teach graduate students, except once in a while, if absolutely necessary, I can get an indulgence on that. But mostly I don't, because I think there are better ways to understand it. So the way that I like to understand it is it's a partial effect. So remember that if I just have a single regressor, so suppose I have a single regressor. So here, a model like this, alpha plus beta, and I'll write it like that. That means lowercase x. Okay, so that's a scalar. Then, let me call this beta 1. Then, of course, the formula for beta 1, as everybody will have known at some point, even if they don't remember today, is the covariance of y and x divided by the variance of x. And then, of course, regression fits the means. So it lies on the sample means. The regression line lies on the sample means, and so the intercept is chosen to make that happen. Well, now what about a scenario where I have lots of regressors? So here's lots of regressors. Whoop. So I have x1 and xk and x capital K. Then each one of those is bivariate, where the regressor for the kth one is xk tilde. So you could compute the regression coefficient on the kth regressor by taking the kth regressor and regressing it on all the other regressors, and then just regressing on that residual. You could do the same thing to y, and you'd get the same answer, but you don't have to do it to y. You only have to do it to x. On the other hand, if you only do it to y, it's not correct. So you could prove that, and I'll skip the details here, but the way to prove that is to take this and substitute it in there, and to use what I call regression algebra. And regression algebra really comes down to one sentence, which is that once you've regressed something out, those residuals are uncorrelated with the things that were in the model, okay? And so since xk tilde was produced by regressing on all the other x's, it's orthogonal to x1 and x capital K. The only thing it's not orthogonal to is x little k. So all those other guys are going to go away. And the only piece that's remained to explain is that the covariance of xk tilde with xk, the covariance of xk tilde with xk is in fact the variance of xk tilde. Because xk is equal to all that other stuff plus that residual, but you're orthogonal to all that other stuff. Okay, so that's the proof of regression anatomy. And when you're teaching undergraduate econometrics, you might trouble to go through this, or at least put it on a problem set. Okay, so this is a case where the property is derived by knowing the answer and then showing that it's true. Okay, but it is a very intuitive thing. Okay, the private school coefficient in the Dale and Kruger regression is the coefficient on the private dummy after I residualize by taking that private dummy and regressing it on all the selectivity groups and saving what's left. Okay, so it's the piece of the private dummy that's not predicted by where I got in and where I applied. And all regressions have that kind of structure. Okay, it's a partial effect. In fact, the step where you create xk tilde, a lot of people call that partialing. Partial out the other regressors. Okay, and that language goes back to older statistical textbooks which thought of partial correlation as something that you should do instead of regression. Okay, so that's regression anatomy. And here's the last step, and I'll let you fill in the details there. Okay, now here's something closely related. I think of this as the golden rule of regression, the most important thing. Oh, by the way, this is not a statistical property. It's true in your data, but it's also conceptually true. This is the definition of a multivariate regression coefficient. So this is not about samples. Okay, this is the way regression is constructed to behave. Omitted variables is the same. Okay, it's not a statistical property, but it's a definitional property, or it's a feature of regression. The omitted variables bias formula, OVB as I like to call it, just tells us how regression coefficients in models that have more and fewer controls are related to one another. And that's very, very useful. So here's an example, again, from labor economics. So this is something like log wages. And here's schooling. And, I'm worried that the fact that more educated people earn more isn't really causal. Okay, because we know that it's, lots of education is kind of the smarter people who get lots of education, as educated people will know. Okay, so maybe I should control for your ability. Okay, it's kind of like the Dale and Kruger story. So I would like to have your SAT scores or something like that in the model that I use to measure the economic returns to schooling if I'm trying to get at a causal effect. But I don't really have that. Okay, I wish I have that, and I can kind of think about what the consequences of having that would be. What am I getting wrong when I run the short regression? So here's the short regression. The short regression has no controls. It's the covariance of y and s divided by the variance of s. It's equal to the long regression coefficient plus the product of these two terms. The two terms are the effect of the controls in the long regression and delta AS. Delta AS is the vector of coefficients from regressions of the elements of the long regression controls on the included regressor. That's a super, super important formula. It allows us to imagine regression coefficients that we can't estimate and say, well, would the regression coefficient that controls for ability, the schooling coefficient, be bigger or smaller than the one that doesn't? Or I could flip that on its head and say, when I don't control for ability, the returns to schooling that I measure are likely too big or too small. Well, that's true as stated. The returns to schooling that I measure are likely too big or too small. Okay, which way should it go? The returns to schooling that I measure when I don't control for ability, well, the difference is the OVB. And the OVB is ability's effect on wages. Since I'm calling it ability, it sounds good. Okay, and so that's probably positive. But then there's the question of how ability and schooling covary. That might be positive as well, in which case the short regression is too big. And that's what a lot of educated people would say. Okay, the short regression coefficient is too big because more able people get more schooling, and I should fix that by measuring ability or constructing some sort of research design. So I use that to think through, and in fact, we've already implicitly used that logic because I said, you know, when I was thinking about the private school effect, you know, the private school kids, they have better Y0s. That's an OVB story. I'm saying P, which is the target regressor that's my included regressor, is positively correlated with things that predict Y0 like ability. And therefore, when I don't control for those things, I'm getting a private school effect that's too big. Okay, so here I actually make my students learn how to say this in words as a kind of a thing to say, okay, as without math, and then think it through and use it. So short equals long plus the effect of omitted times the regression of omitted on included. So everybody should, the homework for tonight is to memorize that, and then I'll ask you about it tomorrow. So when does short equal long? So it says on the slide there's one thing here. So short equals long when the omitted variable and the putative controls are, you know, uncorrelated. That's the delta being uncorrelated. Actually, there's another scenario, okay, which is if the gamma turns out to be 0. But then that's like saying the short regression and the long regression are the same. So that's not that interesting. So the key thing that drives OVB is the covariance between the omitted and the included, okay? And that's a feature of almost all data-driven relationships in the world, and well worth memorizing. Here's just a quick table on the schooling coefficient. This is from much more recent data than the 1980 data I showed you before. This is 2002 using the NLSY. So now by 2002, the returns to schooling have gone way up, and the returns to schooling are all around 13 points. And then what this table shows, again, remember, regressors are not all created equal, okay? The regressor of interest here is schooling. And what I'm showing you here is how the schooling coefficient changes as I add controls, okay? So the first set of controls are a bunch of age dummies, and that doesn't really do much to the schooling coefficient. How come?
Are usually the same age?
Be a little more precise. So use the OVB formula, Sarah.
Okay, so we are not including any characteristics.
So what I'm doing, just to be clear, as I move from 1 to 2, there are no controls in 1, and then in 2 I add dummies for age.
At the time of application, right? So we are
Now
not...
these are people, now they're adults, they finished their schooling long ago, right?
Okay.
And you should be able to use the OVB formula to understand why there's not much difference between column 1 and 2. You see it?
Yeah, because the beta K is almost
Sorry, the what?
How do I say that? The covariance.
Delta? Well, tell me in English. Yeah, not
the
Greek.
Covariance of yi and x to the ki.
Okay, but use real. Tell me in English, not in math. What's the driving fact here? What's the driving fact here? Age and schooling are probably not. They're basically uncorrelated. There's not, you know, people of different ages in the NLSY all get about the same schooling. First of all, the age range in that data set's not very wide. Second of all, you know, most Americans these days, on average, have similar schooling over different age groups. Wouldn't be true for me versus my parents, but it would be true for me and somebody who's 2 years older or 2 years younger than me. So the OVB here is 0. Age and education are uncorrelated, so control for age doesn't effect. Okay, the first interesting one I would say is column 3. So you have to squint there at the note. What is in column 3? I'm controlling in column 3 for parents' schooling. And that turns out that when I add that in, the schooling return for me go down. Okay, tell me what's the story there. Can you tell me what the story is there?
There's some degree of correlation.
Between?
Is that parent schooling?
Yeah.
What we're measuring?
Yeah. So what's the key thing? What's the key fact? There's some degree of correlation between, finish the sentence.
Parent schooling and the dependent. Parent schooling and my schooling.
And my schooling, me being the person that we're observing in the wage equation. It's not actually about the Y, right? It's about the S. It's about the regressor. So the regressor of interest is schooling. And then when I omitted parent schooling, it was bigger than it should be, because one reason that more educated people earn more is that they come from more educated families, and people from more educated families earn more regardless of whether they themselves are more educated. It's a beautiful thing to capture such an elaborate multivariate idea in a very simple way. Okay, so I put my own my parents' schooling in, and it goes down. It goes down even more in column 4. Why does it go down in column 4? Why does it go down in column 4? Can you tell me why it goes down in column 4? The schooling coefficient, why does it go down in column 4?
Yeah, adding a new variable, which,
Let me give you a hint. AFQT is a test score.
so the test score is also correlated with your schooling.
Exactly. Okay, so that's like that's kind of a pure ability thing, right? That's actually the NLSY has some test scores taken in high school. That's because the military uses that data to calibrate their tests that they give soldiers. And so they paid for everybody in the NLSY to take those tests. They paid the Bureau of Labor Statistics. And so now when I control for the test scores as well as the parents, okay, the schooling coefficient is getting smaller. So that's the OVB formula. You're going to lose your phone, Corey. The taking pictures. We'll have to put that up for advisement. You have a copy of the handout. Okay, so that shows you, how, and then you could say, okay, well, maybe there's some other control that would matter in one way or another, okay? So you can use this to think through these regrets. Why do controls matter? They matter because they're correlated with the thing that I'm interested in, and they predict outcomes, okay? And now the last column does something that's interesting and subtle. What's the difference between the last column and the next to last column? The last column controls for occupation dummies. So that's actually a measure of the type of job that I do. And I stick that in. And so once I know that, for example, I'm a manager or a laborer, okay, or something like that, the returns to schooling go down even more. But if what I'm interested in is the causal effect of schooling, it's not clear that column 5 is an improvement on column 4. So that's the bad controls idea. An important thing about the admitted variables bias formula is that it's algebra. It's algebra. It's true regardless of whether the controls that you're adding move you down the road towards a causal parameter. Why wouldn't occupation move me on the road towards, yes ma'am. Why wouldn't occupation move, you answer my question, I'll answer yours. Why wouldn't occupation move me on the road to a causal parameter?
See, I think it does because occupation is correlated with what type of schooling you got.
It is, undoubtedly, undoubtedly.
I was thinking it was causal.
Well, it might be, but there's,
Like, did you go to engineering school or?
no, this is not your college major. This is your occupation. It is. Okay. Think about a world where, I'm told that Australia used to be like this. There was a lot of centralized wage bargaining, and everybody in the same occupation gets the same pay.
Sure.
Is the returns to schooling 0 in that world?
No.
No. So that's why this is bad.
But the engineers get more money than the people who went for 4 years and got a degree in French. So
Could be. But that's a different question. That's really about their majors. Yeah. Okay. But my claim is that I don't really want to take out the occupation differences because The reason you got a good job is you went to school, and that's part of the returns to schooling. So that's kind of a channel for the causal effects of schooling. You were going to ask about the majors? Yeah, yeah, yeah. Okay, but that's a different story. We're not distinguishing different types of schooling here, so it's a constant effects model.
Why do you think it's a bad control and I think it's a good control?
I don't know. You have to think about it.